Alright, welcome to AP Video 15.9. Here we're going to look at solubility, but take a look at how the common ion effect affects that. I did not really throw an objective on the objective sheet about this. I kind of did by doing number 13, but just make sure you know that we're going to look at how the common ion effect affects solubility and do some calculations with it. And then I don't have a practice problem here in the video on this, but we'll also do some practice in class where we work with pH and see how that can affect the solubility of a salt as well. Alright, so common ion effect and KSP. Well, Le Chatelier's principle predicts that adding the common ion to a solution will shift equilibrium to the left. And if equilibrium shifts to the left, basically your starting substance is not as soluble, so you decrease its solubility. So here's a quick little example. Imagine that you have solid silver chloride. That's a precipitate you would form. So let's say it's in water. And if this precipitate is in water, although we say it's a precipitate, it is slightly soluble. So it does reform the ions it came from in small amounts. So it forms silver and it forms chloride, like so. Okay. If you add something with a common ion, so if we add KCl to this equation, this is a soluble salt, and it's going to break apart into K plus and Cl minus. And when you add it, you're really impacting the chloride ion concentration. So according to Le Chatelier's principle, we would be adding more of this, which would cause more collisions between these two things, and they would react backwards faster. So equilibrium would shift to the left, and therefore this stuff does not go forward as fast as it used to, because it's going backwards now. And the solubility, so the S amount here, that's going to be soluble and dissolve, this amount of S actually decreases. Or I should take that back. The amount right here, the amount that it actually turns into the products there, those two ions, decreases. So by adding a common ion, we shift equilibrium back, so it prefers to stay in the form of the precipitate, and you don't get quite as much solubility. So here's some practice calculations with it, and so let's just kind of begin here. So go ahead and break this page in half here, so we can work this out together, and then also break it into thirds, separating these three problems from each other. Okay, so we're looking at the solubility of SRF2. We have its KSP. So first of all, it's in pure water. So in pure water, it just kind of works like this. It's going to be SRF2, and I'm going to leave the solid off just for now, and dissociates into the ions, which are aqueous, remember, and we produce this 2F minus. Okay, so that's our reaction, and then we'll do a little rice table here, and then to kind of make it easier on you guys, this is our rice table. This is the reaction. So underneath this one, we're going to do an ice table, because we'll just use the same reaction above here and just kind of stay in the same columns the whole way down. And same for this one. Alright, so this is a little tricks because we are doing the problem together. Okay, so however much of this stuff is soluble, it's going to actually dissolve that amount completely into nothing left. And we start off with none of these things because it's pure water, so they're not present initially. And we're going to gain S amount of this, and we're going to gain 2S amount of this, and then that means we'll form S and 2S overall. Okay, from that, we will go into KSP equals this particular number here. So 7, we'll start with KSP. KSP equals the SR concentration, ion concentration, times the fluoride ion concentration squared. That's what KSP is going to be here. And then we end up with KSP is 7.9 times 10 to the negative 10th, and it equals, now we can plug these in to the equation now, so it's going to be S times 2S squared. And when we combine these terms together here, it ends up being 4S squared, multiply the S in front there, it becomes 4S cubed. Okay, so solve for S here. We need to divide this by 4, which gets rid of the 4. And then we're going to take the cube root of that there. And that gets rid of the cube. And when we do this, S ends up being equal to 5.8 times 10 to the negative 4th moles per liter. Solubility is always in moles per liter. So that's how soluble this substance is. Okay. Now, when we go to the next set here, we have zero point 0.1 molar SrNO3 as the concentration of a solution. So basically, I'm going to go top here. This SrF2 is also in this solution, and they have a common ion. You should be able to pick it out right away. They both share the strontium part in common. Okay, so let's set the initial. The initial is always going to be whatever is soluble, you lose completely, like so. And now the initial, so I'm working from the reaction up here now. Okay, and we're going to go kind of down the column. So the strontium initially is this amount here. Okay, if you take a look at the dissolving ratio, one of the whole thing here, when it breaks apart, it produces one strontium ion. So it's a 1-to-1 dissolving ratio. So therefore, that is the concentration there. I'm going to write this out really quick because I think it's worth just doing it again. So strontium nitrate, when that is put into water, because it has nitrate present, this is a very soluble salt. So it's going to dissolve completely. It's a strong electrolyte. And it's going to dissolve into one strontium ion and two nitrate ions. So if the concentration of this guy here is 0.100 molar, when it dissolves, it's all gone, and it becomes in a ratio of 1 to 2. 0.100 molar strontium and 0.200 molar nitrate. Okay, but this is what we care about. So that's going to be our initial amount here. So the initial amount of the strontium here is 0.100 molar, and the fluoride here, we don't have it, so it's going to be 0. Now, whatever is soluble for the change column now, whatever is soluble, we're going to gain S amount, and we're going to gain 2S amount here. And then we combine these together, we get 0.100 plus S, and we get 2S. So now these are the amounts we're going to plug into KSP. So let me erase this quick. Okay, and then we're going to plug this in. So KSP is 7.9 times 10 to the negative 10th, and that equals the strontium ion here. So that's going to be this one, 0.100 plus S times 2S, and then that's squared. Okay, so a couple of things we're going to do here. K is very small, right? And when K is really small, the amount of S right here that we add to 0.1 is so small it doesn't impact it. So this is where one of those places where S, when added to something, is going to be negligible. Okay, so just 0.1 is left there. And this part here is going to become 4S squared. So it ends up being 0.1 now times 4S squared. So essentially what we get here is 0.400 times S squared. And we combine that all together. So now to solve this, we take the original KSP, we're going to divide by 0.4, which gets rid of that, and then we take just the regular square root this time, because all we have is squared. So S is equal to that math there, and S is equal to 4.4 times 10 to the negative 5th moles per liter. So let's take a look here now conceptually what kind of happened here, along with the quantitative part. When you have a common ion, so when the common ion is already present initially, what that does is it decreases the amount of solubility, because it kind of wants to shift equilibrium back this direction. So look at our initial solubility in pure water right here. About 5.8 times 10 to the negative 4th molar was soluble. And now with the common ion effect in place, times 10 to the negative 5th. Now less amount of our SF2 up here is soluble. So when you add a common ion, it decreases the solubility. Okay, I'd like you to try the next one out here. Plug in your initial amounts for everything, whether they have anything, and try to solve this last one by yourself here, and then unpause when you're done to see the answer. Okay, so here we have 0.4 molar sodium nitrate or sodium fluoride. So the common ion here is going to be the fluoride, and the dissolving ratio is 1 to 1. You start with one of these, and you make one of each ions. So the concentration here is the concentration of fluoride. So today in our practice problems, these concentrations I gave to you were the concentration. It is possible though, if it didn't dissolve in a 1-to-1 ratio, you might have to double things or triple things potentially, so watch out for that. Alright, so whatever is soluble for our starting substance, going back to the top here, SRF2, whatever is soluble, we'll lose it and become 0. Our initial amount of strontium, going back to the top here, initial amount of strontium is 0. It's not part. But the common ion right here, we do start with some of the common ion of fluoride. Now, whatever amount we lose here, we're going to gain in our ratio. So we're going to gain S amount of this, gain 2S amount of this. So you end up with S and 0.400 plus 2S. And now we can plug these equilibrium amounts here into the equilibrium expression for KSP. So KSP is 7.9 times 10 to the negative 10th, and it equals S. That was the first one here. And now we plug in the last one here, 0.400 plus 2S, and all of that is squared. Now before you start solving here, keep it easy on yourself. When you add S or even 2S amount to the initial amount here, S is so small because K is small, so this is going to be negligible. Okay, so really what we have here is 0.4 squared and S. So 0.4 squared is 0.160, and that times is the S here. So combine the 0.4 squared and the S there, we get 0.16 times S. So we're going to divide this by 0.16, and that will be the solubility. Solubility is equal to 4.9 times 10 to the negative 9th moles per liter. Alright, so solubility, again, when the common ion is present, so when sodium fluoride contributes fluoride in the strontium fluoride reaction, you have some of this present initially, which therefore decreases solubility. So in water it was 10 to the negative 4th. Not in water, in this sodium fluoride mixture, that common ion effect, it decreases the solubility a lot again. And as you can see, common ion effect does impact solubility. It does increase it. Alright, good job.